Right. So just to run over quickly some of the things in probability. We know how to find probability, right? This is how we find probability of A and B. We know all probability between 0 and 1. We know that if probability of A and B is 0, then it is said to be mutually exclusive, right? We also know that if the probability of A and B is equal to the probability of, sorry, if the probability of A plus the probability of B is equal to the probability of A and B, then we have independent events. Otherwise, the events are conditional, right? One depends on the other. Right? So quickly just to show you all the little sets. By a set, remember the little notations, right? Here we have an example of a tree diagram. And a way to always remember that from every branch probability sums to 1, and it shows you here how to find conditional probability and so on, right? Remember, a tree diagram is an example of what? Conditional probability, right? One is dependent on the next. So the second branch here is dependent on the third branch, will be dependent on B and E and so on. Right, next thing we need to remember about discrete variables. Discrete variables, these probabilities always sum to 1. To find E of x is x by P of x, variance E of x squared minus E of x all squared. How do we find variance? How do we find E of x squared again? You sum x squared multiplied by probability, right? And you have the formula here for variance and so on, right? Next. Just a small rule to remember about E of x. E of ax plus b is E of x plus b. So if I ask to find E of 2x plus 3, it will be 2E of x plus 3, right? So just some quick rules to remember. These are the conditions of binomial. This is how you write a binomial, how to find the probability. Okay? Just some small quick things to remember. And to find the expectation of a binomial, n by p variance n p q. Please remember that if the binomial gets too big and is more than 15, what has happened? You have to approximate it to normal, and you have to apply what? Continuity correction, right? Don't forget the continuity correction. Then you have your continuous variables. That's basically to get the probability, the area under the graph. But as I said in unit 1, there's no integration. So most likely you will get shapes like the one underneath here where you can find the area. So it is a trapezium and this looking like a rectangle, something like that. Right? And if you add up all the probabilities, you should get one. That's okay? So the shapes that you will get, of course, the shapes that you will get will be things that you can find the area of. All right? Of course, we should be able to integrate as well, right? Just in case, let me tell you that. Then you have your normal distribution. This is the shape, mean mu, variance, sigma squared. We all know that we can't use that table to get any values, so we have to standardize. Okay? So in order for us to standardize, we always minus the mean and divide by the standard deviation. Then we can go to the table and then we can go to the table and work it out, right? Right, and after that, we just talked about applying continuity correction and so on. So those are some of the things I want you to remember. Right, let's do a couple of questions and then we start 1-3. Online, where do the SPN, where do the SPN, no? On board is SPN with some of them here. Right, it's memory years that we did now. If it does 19 as yet, 29. Oh. I think we did part of 9. 40. Let's do this last people after 19 minutes. The 29th. Number 3. 19, 3 part C. What kind of distribution is this? Substable. What's the answer? Two? No? 19. What's the final answer here? Right? But, but. Right, and now they want the probability distribution, right? So we have X, the probability of X equal to X. So you're throwing it 3 times, right? The random number, X number of times it will hit in the three tosses. So you can hit 0 times, you can hit 1, you can hit 2 times. Or you can hit all 3, right? That's okay. So the probability that it hit 2 times was 2 nines. Probability it hit this 0 times was how much? 1 time. And last one. One on? Inside. Yeah. One. Alright, so you have to work out 4. So take a little while, but you have to work out 4. Or work out for 3 and then -1 to get the last one. Find E of X. Find E of X. Finish. So you should have E of X already. Right? That'll be 0 plus 4 nines. Plus 4 nines again. Plus 1 Q over 9, 1 9. So I got 1. But I got 1. Yeah. Last thing. Look at those last two parts there. Well, no, but you don't have to finish it in SIP. Right? But you already have the distribution, so n was what? 3. And Q was what? Work out that fast, they gave you E of Y and they gave you variance of Y. You're almost done. So the first one, you should have 3 e of y plus 2. So that's 3 by 3.8 plus 2. How much is that? 13 point. Next will be, remember, it's 3 squared, right? By variance of y. So that's 9 by 2.16, which is 19.44. That's okay. So set this equal to. All right. Okay. Just some small things for you to remember, right? What do you ask after? You did number 4E already? You did 4E already? All right, let's do 4E and B. You did C, normal distribution, yeah? All right. Let's do E. Right, part 3 is, so state 3 reasons why the experiment above may be modeled by a binomial. So if you look back, I gave you some conditions. Use the conditions to answer that. And then state the parameters and work it out. The 3 reasons why the experiment above may be modeled by a binomial. What you all said? Right here, so it either is a picture card or not, right? So a success is a what? Can you define it? Picture card. So a success is a, so there's a success, picture card, failure is non-picture card, right? What else? Fixed number of tries, right? You have 12 number of tries. What else? Oh, the next one, right? What else? triggered. You have one more. So it can be repeated a finite number of times. All right. State the parameters of the distribution. State the parameters. It will be x follows a binomial of n what? N is how much? And what's the probability of getting a picture card? Right? Remember, you have 3 picture cards per suit and you have 4 suits, right? And don't know if I said it, but remember, you have to learn about cards, right? They're expecting to know some of these things, right? So 12 and 52. 12 and 52. Next part B. Oh wait, not related. Yeah, not related. Check part B.
What parts of it?
What are we doing after? We're doing B and C. So we did D already, right? We did D already. Yes, B and C then. What you got here? So a driver believes that 73% will pass their driving test on the first attempt. 15 students who will take the driving test for the first time. The number of students expected to pass. That's 70%, 73% of 15, and you're up 11. That's all right. Expected. So N by P. Easy marks. Last 2 parts are done. Right, so they want exactly 12. So the probability of X is equal to 12. That is 12, sorry. So that'll be what, 15C12 by 0.27 to the power of 3 by 0.73 to the power of 50. Well, sorry. How much you got there? How much? 0.205. Right, last one. I looked up a little bit of normal distribution and we got. Then we start the next one. Right, it's a little bit of the normal, right? Right, so the last thing we have to do, they give us a normal distribution. X follows a normal distribution where the mean is 12 and the variance is 4. Find the value of C such that the probability, so let's see if we can do this last part, right? Probability of X is more than C is 0.9583. So since it's more than and the value is bigger than 0.5, it means that C is what? Positive or negative? Negative, right? So it means C is outside here. More than, right? So what do we do? Well, then minus C will be equal to 1 minus. I should write a little bit different, so you will end up with 1 minus 5 What's the next statement I have to write here? Statement, huh? What do I write here? What do I write for this part of it here? After? So after start with standardizing before I go to the value, right? That's okay? Hold on, let me just scroll up there. Any answers online? I realize I have a online today. But it's saying anything. A little small thing, I'm severe. Right. So as we said, probability X follows a normal distribution mean 12 variance score. So when the probability of X is more than C is equal to 0.9523. So the first thing we do is we what? We standardize, right? So what do we write to it? Probability of Z is what? Always write statements part of it. No, not yet. Quite a bit. No, what do we write here before we started? So it should be what? C minus, right? C minus 12 and 2, right? That's okay? Where does the minus sign go? How we know it's minus again? Right? And it's more than, and the value is bigger than 0.5. Right? So we know it's minus C. Okay? So we know it's minus C. So what do I write now? What do I do now? So it tells me that phi of this value should give me what? Phi of this value, that's not for the right. Phi of this value should give me minus 9583. Where do I put the minus sign? Do I put the minus sign in front of the C or in front of the whole thing? In front of the whole thing. Okay? Because it's this value. It's this entire value here, right? That entire value there is the value that we're going to read off here. That's okay? So I should write minus C. I should write minus 12 on 2. Right? Now we have minus C minus 12 on 2 is phi inverse of 0.9583. How much is that? 1.731. So carry it across. You'll get C minus 1212 is minus of this. Multiply by 2 and add 12. How much is that? Here's how much. 8.53. Yeah. Okay. So two things I want you to remember. I want you to remember that when it's more than and a value bigger than 0.5, the value negative, and where to put the negative sign. Okay. All right. That's the end of that for now. Online, anybody got that? 8.53. And what you can do now is you can plug back in 8.53. We'll go this and just make sure you get it out. You want to just check it back and see. Right? You can plug in 8.53 in here, minus it from 12, divide by 2, and then we go 1 minus balance square. And 1 minus read off the value. Just to make sure. So when you find pi of 1.71, it should get the answer. All right. So now we're moving on to the module 3 part of it, right? I just introducing the first part. I'm not going to pi into it. So now that we collect data, now that module 1 is about collecting data. Module 2 is about learning about the distributions that we're going to use. Right? Module 3 now is where we start to make inferences. We start to actually calculate values and make little inferences, right? So let me just give you an idea of what module 3 is about. Right. So in module 3, we're going to start to create estimates. So we're going to find a way to estimate and see if something is true, right? So the first thing we do is we find point estimates. Right? So we try from a population can have 1 million people in it. We're going to try to get an estimate from it. Okay? So one of the estimates that we can get from a population is a mean value. Right? We can also get a variance value or we can get a proportion value. We're going to learn to estimate these actual values. They are called point estimates. Right? We're trying to estimate the point. After we do that, the next thing that we're going to do, if we can't estimate the actual point, we are going to try to estimate an interval. Right? We are going to try to get an interval where we think the mean might lie. Right? So the mean might lie between these two values here. We're going to try to get something called an interval, or more formally known as a confidence interval. All right? So the point estimate, a confidence interval, Mikhail, and the last thing that we're going to try to do is we're going to do something called a hypothesis test. So we're going to assume something, right? Something like this. We're going to assume the mean behaves like that. Otherwise, if we're wrong, the mean behaves like this. Okay? So we're going to actually try to find the actual mean, find a value for it. Then we're going to find an interval where it might exist. And then we're going to create a hypothesis where we think the mean is this value. But if we're wrong, the mean less than a particular set of values, or more than, or not equal to. Okay? That's where we reach now. We reach a point where we need to start to take our data or take our values and start to do some estimation. And then from the estimation, we can make an inference. We can say, okay, well, the mean is this, the mean is not that, and we can conclude a few things. Okay? And at our level, we only focus on mean or proportion. Right? But you have other tests that you can do. You can do like a variance test, after the different tests you can do. Alright? But for now, this is all we're gonna do. Right. So before we do anything, right, we already know just now, right? How to understand something that we have to look at. Remember, we are trying to estimate everything. Right? We are trying to make an attempt to estimate everything. So technically, we don't really have a distribution. We don't know nothing about a distribution. So let's say we have this population to work with. Right? We have this population to work with. And we take a sample. And then we find mean of this sample and the standard deviation or the variance of this sample. Think that's enough? You think that that sample is enough for us to talk about population? So what they do is they take a large number of samples. Some might overlap. They try to find a large number of samples. So we end up with a whole set of X bars, X bar 1, X bar 2, or mu1 or mu2, and so on, right? We have a whole set of X bars here. A whole set of X bars. And what we create now, of course, this will give us more information, right? This is now a new distribution, right? This is a new distribution that we're looking at. And this distribution is called the distribution of sampling means. Right? This distribution, just like the original, if it were normal, will also be normal. But E of X, right? E of X won't really change for this distribution. It will be mu. But for this distribution, the variance, okay, I will show you the proof one of these days, right? But the variance for this distribution of means, sorry, will be sigma squared on n. So this distribution, the variance will change a little. So now, any estimate that we're going to use, it will come from this. So our new distribution, which is X bar, will still be normal, but the mu is the same, but the variance is sigma squared on n. Right? Originally, the data came from something that was this. But we don't know these things. We don't know it. So because we don't know it, we're going to have to create all these samples and create something called a distribution sample of means. Right? And then from this distribution, we will say, okay, well, here's what. This sample distribution of mean will also be normal, but the mean will be mu, and the variance will be sigma squared on it. Okay? So every time you see they ask you to find the sample distribution of means, this is all we're using in module 3. You don't use this anymore. You use this. Because everything we do is estimated from this population. This is distribution we're using from now on. Not this, sir. We're using this distribution of sample means to calculate everything. Okay? So what's the difference? The mu is the same, but the variance is now sigma squared on it. All right? So that's a new distribution that we're going to focus on. Whenever you hear sample distribution of means, that's what we're talking about. You going again?
Go fast now.
Alright, so I want to understand you follow what is sample distribution I mean. What it means. There's a whole set of means that we took from all these samples to give us a better idea of how the population really behaves. So for this distribution, we only focusing on finding we're interested in how the mean behavior. Because our distribution only have means in it. So if I ask you to find the probability of X, you can't use this. What I'll ask you for is to find I'll ask you to find something like this, right? Find the probability that the mean is more than 4 or something like that. Right? And once you see this, this should remind you that you have to use the sample distribution of means. Right? As I told you before, we're trying to get the point estimate of the mean. We're trying to get the confidence interval of the mean. We're trying to get the hypothesis testing of the mean. So if we're using the mean for everything, we have to get a distribution and how the mean's behaving, right? And that distribution is what we call the sample distribution of means. All right, online, are you okay with that? Keely, Stefan, Annalie. We'll be doing now, Keisha. Keisha, there too. Yeah. All right, nice. Right, I said it's time for the holidays, right? I might have to ship all a little bit more. I don't want to put all on the same day physics and zero. Right, but tell her how I will do it, right? For the school, the last week of school? Last week? I'll tell you, I think you can do the last week of school. So you're free now. All right, so let us try something on this. Right? You'll recognize that for all of these, we're still using the normal. Okay? So we're going to do calculations still using the normal table. Right? When the normal values get small, I'm going to introduce a new table called T distribution. Right? When it gets small. When it's a little too small, we use something called T distribution. N will be the number of subsamples that we take. N will be the number of samples that we take. Right, you reach back. Let me start now. At a school, right? We are trying a small example on how we'll use this, right? At a school, the masses of the female students at a school, the masses of the female students can be modeled by a normal distribution. With a mean mass of 70 kilograms and a standard deviation of 5. At a school, the masses of the female students are modeled by a normal distribution with mean mass 70 kilograms and standard deviation 5 kilograms. Full stop. Five female students are chosen at random. 5 female students are chosen at random. Find the probability that their mean masses, Their mean masses is less than 67 kilograms. All right. Yeah. So I'll do this one to make sure you understand what to do, right? So number one, what they ask us for? The probability that the mean mass is what? Less than 67. So because they tell us about the mean, we need to know how the mean behaves. So the mean will behave as a normal with mean mu and variance sigma squared on n. Right? And we know this from before. They told us that x follows a normal with mean what? First line. 70 and standard deviation of pi. Right? That was where the original data came from. So now this sample distributions of mean will be x bar follows a normal distribution. Mean is still 70 and variance is 5 squared over. How many we took? 5? 5. That's okay? Right? We chose 5 people, right? We chose 5 females, right? Nice. So now, how do we find the probability of x bar is less than 67? We treat this just like how we were doing it before. X is, we have to standardize that. So we're going to standardize. And we will get the probability of z is less than 67 minus 70 all over what? What value we use now underneath here? Do we use the old 5 squared? We use this value. Okay? 5 squared on 5 is 5, right? So that'll be the square root of, but I just writing it like this, right? So you remember how I got it, right? This is the square root of this. Right? Because they give me the sigma. That's more there now. Where's this? Oh, it's root 5 anyway. How much? Minus 1.3. And then go to your table. Right? What does this equal to? Less than minus 1.34. It's the same as what? Right? It's the same as 1.34 on the right side here. So that'll be minus pi of 1. Minus pi of 1.34. How much is that? I'm not sure about. Yes, standardized. Yeah. This will change. This is already changed. But we need this to help us figure out what we're doing here. less than negative means that this small area. And because it's symmetrical, this will be the same as this. Remember, there are no negative values. Right? How much you got? 1 minus pi of 1.3. 4. Zero point. Online. Anybody get that? You just ever consider that it didn't come from a normal? What you would do? Because suppose it didn't come from a normal. Suppose it didn't come from a normal. What will you do? Convert it to normal, we'll close. Highest convert it to normal. What you do? Remember CLT? Well, sorry, I said remember. I'm going to feel the central limit theorem. Let me share. Okay, so here what you just do. I don't know if you remember from what I told you, all right? If you collect a large number of values for almost any distribution, it will look like a what? It will look kind of symmetrical again, normal. So what you do in cases like this, when n is large, you do something called central limit theorem. That distribution will behave like a normal, regardless of what. Right? So when n is big enough, it will follow a normal. So what she's doing questions like that, where you don't know where it came from, or what kind of distribution it came from, you state by central limit theorem, right? I'll give it a theorem next week. I won't go into that now. All right. Let's try one more like this now. Let's try one more like this. What's the key thing to let you know that you have to do this? That you have to find x bar is that part there, change distribution. What's the keyword you're looking for? Mean. Right? Keyword is mean. And this is in module 3. So you don't see this in module 2. So don't make the mistake in module 2 and use variance as sigma squared on it. This is module 3. Okay? Everywhere you see mean, which is every question in module 3, you have to convert it. All right? What I do sometimes is this, right? I just wrote it here for you for a reason, right? But what I do sometimes is I don't worry with this anymore. I work out this value 17, 5. And then underneath here, I write root 5. Okay? So I'm not interested in that. I'm using this value here to help find my standard error. It's called a standard error. This value here is standard error. Okay? So it's important that you're not looking anywhere else. You know, sometimes in exams, you might see something like you might think about this, right? You might think about doing taking your sigma from here because you're seeing sigma. So what I want you to do is after you write this, you can totally ignore this and just focus on this distribution. Okay? So this is the n, this is the value goes here. Square root of this goes in here. All right? So common mistake, people just do this perfectly. They do every single thing here, right? When it's check back, the value they use here is the wrong thing. Okay? And I'll tell you in the 2 class look on this. How about this? All right. Let's try one now. Okay, that's the one graph last thing. I don't know how school at the teacher like but there was not money. This year we didn't have that. Alright, let's try this last one here. It's a little bit different, huh? Try this here from up. The distribution of a random variable. The distribution of a random variable is such that x follows a normal distribution with mean 25 and variance 340. Is such that x follows a normal distribution with mean 25 and variance 340. Find the value of n. Find the value of n to two significant figures. Find the value of n to two significant figures. Find the value of n to two significant figures, given that the probability of x bar is more than 28. Given that the probability of x bar is more than 28, is equal to 0.005. Right? X bar is more than 20, it is equal to 0.005. Huh? 340, I give you the variance. Take your time, right? What different now is that I gave you the probability, but I didn't give you n, right? Right, so you kind of work backwards and find n. Online messenger value is the last thing we do. Keshav, I want to get your answer. Yeah, 2 minutes. Yeah, I finish up this now. Go ahead. Go ahead. So we'll get the probability of X bar is more than, sorry, you're gonna standardize it one time, right? Probability of Z is 28 minus 25 all over the square root of 340 on N is 0.005. So because it's more than and the value is so small, we know it's there. So that means 1 minus 5, it means that this is positive, right? 1 minus 5 of 3 over the square root of 340 on N is equal to 0.005. You can move across the things there, and you'll get 5 of 3 square root 340 on N is equal to 1 minus this, which is 0.995. Yeah? Where you get lost? Right? What next? Move across the 5, right? So it will be 3 over the square root of 340 on N is phi inverse of 0.995. How much is that? Can we should choose it? How much you got?
What were the line before?
Oh, line before. Okay. How much you got? 2.574. Yeah. Then just cross multiply and solve. Or if you want to get rid of the square root, square both sides. It's up to you. When you want to get rid of the square root. Right? When you get rid of the square root, we will end up with 9 over 340 on N is equal to 2.574 squared. We could flip up the N and then cross multiply, right? Flip up the N and then cross multiply. You'll get 340 by 2.574 squared all over 9. Two significant figures, right? How much? 250. Sorry. Anybody get our line? We'll use continuity correction whenever you convert in a discrete distribution to something continuous. So whenever you're having unit 1, whenever you have a binomial, and you convert the binomial to something like a normal. Whenever you do that, that's when you use continuous. Continuity correction. The word continuity correction means you're converting from or towards continuous distribution. Have you looked at that? All right, so that's it. So this is your intro into sample distributions of means, right? Once you start seeing mean, don't make the mistake. Once you start seeing mean here, don't make the mistake and use the wrong distribution, right? Once you see mean, you're using sample distribution of mean, which is this. Right, that's the most important thing from today. And then we'll start to break up the different conditions now when it's not a normal or it's too small, right? Down with all those things, right?